Okay, so today we're going to talk about rotational kinematics. So we're going to start moving on away from linear motion and towards rotational motion. This is one of our first topics that we're going to talk about. And what's nice about rotational kinematics is it is not that different from linear kinematics. The idea is if you have an object that is moving in a circle. So let's say I have a disk. And maybe I put some objects on top of the disk at different positions. And let's say I rotate all of that together, and I've got the center right there. They are all going to move it at based on angles. So if I take a look, and this is the starting position that they are at some point in time later, they're going to be over here, having traveled through a circular arc. It's not in the right spot. They will all travel through some circular arc to their new positions. Now, it's going to take some delta t for that to occur. Now, they're going to travel at different linear speeds, because they're going to go different distances in that same amount of time. But what's true is they all travel through the same change in angle. So when we're talking about rotational kinematics, we're not talking about the linear distance traveled. I'm not talking about some position x. I'm talking about some arc, theta, that is traveled through. So I'm going to redefine my variables in terms of theta. So I have basically delta theta as my new fundamental kinematic variable. This is going to be our angular position. We're looking at a delta theta because it is a change in the angle. Generally what we do is we set theta equals 0 to be a reference angle. In pre-cal, it's traditional to set theta equals 0 to be along the positive x-axis. But technically, I can define any angle to be my starting angle. So if I wanted to define this as theta equals 0, then I could define this position as theta. And then my delta theta would be theta minus 0, which is just theta. So sometimes instead of seeing delta theta, you'll just see a theta. If you see that, then basically what they've assumed is that wherever that started, it started at 0. Now, if I were to keep rotating through this, keep going through those angles, if it keeps rotating, the angular displacement will move past 360 degrees or 2 pi radians. And actually, we work in radians, so our angular position should be measured in radians. So this is one time where your calculator needs to be in radians instead of degrees for physics. So if I start at theta equals 0 and I go through 2 pi radians and I go through again, I've traveled 4 pi radians. So my angular displacement would be 2 pi radians because that's the angle that I've traveled through. Even though I ended where I start, my physical displacement would be 0. My linear displacement would be 0 because I end where I start. My angular displacement going around the circle 2 times would be 4 pi radians. So theta is just position, kind of like x was position or y was position in radians. And then delta theta is angular position. So let's say that I travel through some delta theta in some amount of time. Well, the rate of change of position over time, delta theta over delta t, would be my angular velocity. It's the rate of change of theta over time. That angular velocity would have units of radians per second, because it's displacement over time, and we give that symbol the Greek letter omega. So this is the Greek letter omega. It is a lowercase omega, because capital omega looks like that. So this is lowercase omega. It looks kind of like a butt, butt cheeks there. Kind of helps if that you do not make it a regular W if you can at all avoid it. So it is a lowercase letter. So if we kind of look at our kindergarten lines here, it should be a lowercase omega. And we'll go through there. So please don't call it W. Please call it omega. You need to get used to using the proper names for the variables. So kind of like we have mu, now we have omega. So omega is our angular velocity, and technically, if I'm using this definition, this is my average angular velocity. So because I'm taking a look at what my average angular velocity was over that time. Now, when we are thinking of kind of average values, it's just the delta theta over delta t. Remember, this equation only works if you have constant acceleration, or actually if there's no acceleration. If no angular acceleration, which we'll talk about in a minute. So we're basically just going through everything we did with linear kinematics. We are just now doing it with rotational kinematics. So we can just define omega to be our angular velocity. In radians per second. And that average angular velocity can always be calculated as delta theta over delta t if you have no angular acceleration. So as long as you're moving at a constant speed, that works. Otherwise, it just gives you an average. So this works as long as always if you're going at a constant speed. Otherwise, it just gives you an average value, not an instantaneous value. So I could then maybe at this position have some initial angular velocity value, and at this time later I could have some other value, so that maybe I have accelerated. So omega is greater than omega 0, so it's gone faster around the circle. Well, if I go faster around the circle, then I'm going to have a change in omega. So my delta omega would be omega minus omega 0. So that would be my change in angular velocity, would be my final angular velocity minus my initial angular velocity. Once again, we're using the variables as they are on the AP Physics 1 formula sheet. And if I do that in some particular amount of time, then this is the definition of angular acceleration, which is the change in angular velocity over time. And that would be radians per second squared, because we've divided by seconds again. And we give that variable the Greek letter alpha. So that's just like the alpha and omega kind of type idea. Kind of looks like a fish, so you should get practice kind of doing that. If you have some sort of curvy A type thing that you normally write with, you need to find a way to differentiate between an A and an A. A and alpha. So this is the Latin letter A. This is the Greek letter alpha. So however you do that, because, and sometimes in type it gets kind of confusing to tell the difference in depending on what font you're using. So you need to find a way to establish it, because we will be working with both linear acceleration and angular acceleration as we go through. And technically, based on this definition, this is technically our average angular acceleration. But since we generally assume that our acceleration is constant, this definition is going to work. And actually that's one of our kinematic equations. So this is assuming that our acceleration is a constant. Otherwise, if our acceleration is not constant, it is an average value. So we now have another kinematic variable. So we have alpha is our angular acceleration. All right, so we now have all of our rotational kinematic variables. So we just went through essentially 2 weeks of linear motion that we did in AP Physics 1 with kinematics. You could do graphs with this, so I can have theta versus time graphs. You know, and the slope would be omega. I could have velocity versus time graphs, angular velocity versus time graphs, and so forth. and my slope would be alpha. So everything you learned about linear kinematics works in rotational kinematics in terms of these variables. Now, the one thing we haven't talked about is these are vector quantities. So if they're vector quantities, how do we do vector directions? Because technically, my linear vector is constantly changing as I move around the circle. So what we do is we generally assume, and this is consistent with pre-cal, is that the counterclockwise direction is the positive direction. So if an object is moving in the positive direction, that means, so if I'm rotating counterclockwise, that means theta is positive, omega is positive. And once again, you can't tell alpha unless you know whether you're speeding up or slowing down. So your alpha would be positive if you're speeding up, and your alpha would be negative if you were slowing down. So we know that that is kind of consistent with pre-cal. It's consistent with linear kinematics, where you don't know the direction of alpha because that's dependent on force, is the direction of alpha, but you can tell the direction of alpha based on whether you're speeding up. So if you're moving in the positive direction and you're speeding up, your angular acceleration is also positive. If you're moving in the counterclockwise direction, but you're slowing down, your alpha is negative. So if you're moving in the clockwise direction, we define that as negative. And in that case, theta would be negative, omega would be negative, and then alpha would be negative if you're speeding up. And alpha would be positive if you are slowing. But what does positive mean? Well, technically, the theta direction is the positive direction, kind of like that. But if you go counterclockwise, but omega is weird. Technically, the omega, the velocity vectors and the angular acceleration vectors do not actually point around the circle. And probably theta doesn't either, but it's really important for these two. And it's kind of something to keep in the back of your head, because technically my direction, while it's still always counterclockwise, it's still technically changing. And in order for my angular acceleration to be constant, it needs to be pointing in one direction. And a lot of this comes down to vector calculus, but basically, if you were to curl your fingers in the direction of the rotation, that's the direction that omega points. So technically, if I have, if I look at like a vertical axis here, like that, and I'm moving in some sort of counterclockwise circle, so if I'm going counterclockwise and I were to wrap my fingers around, my omega vector would actually point up. So if the object is rotating in the counterclockwise direction, my omega vector actually points up. So if this is the XY plane, my omega vector technically points in the positive Z direction, up out of the page towards the camera. And then if you're going in the opposite direction, so if I was going in the, oops, that'd be the same direction. If I was going in the clockwise direction, if I were to curl my fingers in the clockwise direction, kind of like I'm holding that axis, my thumb points down. So that would be a negative omega because we're in the clockwise direction, and this would be a positive omega because we're in the counterclockwise direction. So a clockwise rotation, a counterclockwise rotation does mean positive omega, but technically omega points perpendicular to the axis of rotation in the positive direction. And then if I wanted to determine alpha, it would follow these rules. So basically, if I was slowing, if I was, say, speeding up, let's say I go back to just having this purple circle here. And let's say I was speeding up around the counterclockwise direction there. My alpha would point up if you're speeding up. And alpha would point down in the negative direction if slowing. So you can always keep at the back of the mind that counterclockwise rotation does mean positive omega. And if I'm going counterclockwise and alpha, and I'm speeding up, alpha is also positive. They're both positive, but technically they're both pointing perpendicular up out of the page. So that's just kind of something to keep in the back of your mind, just in case they ask, where is the vector itself pointing? I can't draw a curved vector. The curved vector doesn't exist. So that's the basics of our kinematic variables. So let's take a look at our kinematic equations. This is actually really awesome because we don't have to learn much new. So in the linear, our main kinematic equations are omega equals omega 0. Oh, no, sorry. Ooh, there we go, sorry. All right, so in the linear terms, we have v equals v0 plus a times t as the first equation on the formula sheet. And in terms of rotation, we have similar equations. So if I have v equals v0 plus at, well, remember that this equation was just a equals change in velocity over change in time. That's where that equation came from. Well, we defined alpha as change in omega over change in time. So really, these equations are nearly identical. We're just changing out rotational for linear. So I can rewrite this kinematic equation in rotational terms as omega equals omega 0 plus alpha t. Wow, isn't that so crazy? The second linear equation that is on the formula sheet is x equals x0 plus bx0t plus 1/2 axt squared. And what do you know? When you rewrite this in rotation, it is going to be theta equals theta 0 plus omega 0t plus 1/2 alpha t squared. Ta-da! What's amazing is they actually put those two equations on the formula sheet for you. The third equation was omega squared is equal to omega 0 squared. No, go back. The next equation was v squared equals v0 squared plus 2a delta x. Technically, remember they write it x minus x0, but I prefer the delta x version. And then in angular terms, this would be omega squared is equal to omega 0 squared plus 2 alpha delta theta. Once again, you could do theta minus theta 0 to be consistent. But here's the thing, these three equations are on the AP Physics 1 formula sheet, but only the top two are. But it doesn't matter because you already know this equation. It's on the sheet, so you just have to switch it. So even though it's not written there for you, you know it. Remember, the fourth equation isn't actually on the formula sheet. It's that your displacement is equal to your average velocity, which is 1/2 v0 plus b times our change in time. Remember, this is our definition of average velocity. Just 2 velocities divided by 2, you know. This equation's not on there. It would have an equivalent equation though, which would be delta theta is equal to 1/2 times theta 0 plus theta times delta t. And remember that always with these equations, you work in radians. So you might have to change between radians and degrees. And remember, these equations only work if alpha is constant. Sorry, those are 2 last-minute reminders.